Everyone, welcome back to my channel. In this video, we are going to start chapter 2, Lagrangian theorem. It's really important because here we learn how to handle things in the Lagrangian formalism, not just particles. We will see how to construct Lagrangians, how to identify currents, and how to use Noether's theorem to connect symmetries with conserved quantities. Mastering this kind of exercise is essential if you want to feel comfortable with modern theoretical physics, where everything is written in terms of fields and symmetries. And to finish the chapter, I would like to make contact with a very familiar object, the electromagnetic field tensor, which is a beautiful example of how all of this formalism comes together in a real physical theory. So let's get started with Lagrangian field theory. Begin with the first exercise of chapter 2. We are asked to find the equation of motion for a forced harmonic oscillator whose Lagrangian is this. Here, alpha is a constant that represents an external driving term, a simple way to model a constant force acting on the oscillator. Now we solve the Euler-Lagrange equation. Taking the derivative with respect to x dot and x, we get the following in the box. What is inside the box? Simplifying, we take this familiar form. Mx double dot plus m omega square x minus alpha equals 0. This is the equation of motion for a harmonic oscillator under a constant external force. The term alpha x shifts the equilibrium position of the oscillator. In other words, the potential minimum moves from x equals 0 to x equal alpha divided to mw squared. We can rewrite the potential energy as this that appears here. This shows that the system behaves exactly like a normal harmonic oscillator, but centered around a new equilibrium position determined by the external force. It is important to remark that the constant term alpha squared divided 8mw squared doesn't affect the equations of motion, it's just an energy offset. What is that the Lagrangian now harmonic whose equilibrium point has shifted to x0 equal alpha divided to mw squared. This shift is the physical effect of the external force we introduced earlier. Now, if we define a new coordinate, x prime equal x minus x0, the motion simplifies beautifully. The derivatives remain the same, x dot and x double dot. In these new coordinates, the Lagrangian becomes this, which is exactly the standard harmonic oscillation force. So the constant force doesn't change the dynamics, it only shifts the origin. Now that we've seen how a simple coordinate shift restores the usual Lagrangian form, we move to the next exercise. Here we will consider a field Lagrangian, given by this expression here. We'll write down the field equations, the canonical momentum and the canonical momentum density and the Hamiltonian. This is where the formalism of classical mechanics evolves into field theory, the language of modern physics. Let's start by writing the Euler-Lagrange equation for the field. This is the field theory version of the same principle we use for particles, except now the derivatives act on the field phi itself. Next, we expand the derivative of the Lagrangian. The only term that depends on partial sub mu phi are those involving the kinetic part, partial sub mu, partial super mu. So we take the derivative with respect to partial phi, not mu, because careful not to repeat the same meanings incorrectly. That's why I have liked them. We will change one of them to avoid confusion. Now the derivative acts only on the term that contains partial sub nu of phi. To handle this properly, we lower the index using the metric tensor. This step ensures the expression remains covariant. Now, when we take the derivative partial sub nu of phi, we get a Kronecker delta super nu sub mu, This delta effectively replaces one index with the other, simplifying the expression. After simplifying, we obtain partial supermu of phi. And applying the derivative again, partial sub nu of partial supermu, we get this expression here. The second derivative of phi with respect time to times minus the Laplacian. This part is the wave equation for a free scalar field, the foundation of field dynamics. Pause the video here if you want to copy the details. Now we take the derivative of the Lagrangian with respect to the field phi. The kinetic term doesn't depend directly on phi, so only the mass and potential terms contribute. That gives this minus m squared phi minus the partial of the potential with respect to the field. This represents how the field interacts with its own mass and with the potential. Next, we combine this result with the derivative found earlier. Putting both terms together give the full Euler-Lagrange equation for the field. This box equation is the Klein-Gordon equation with a potential term, the fundamental equation of motion for a scalar field. In part B, we are asked to find the canonical momentum density, P of x. To do that, we first write the Lagrangian in terms of the position vector x and time t. When we derivatives, we get this expression, 1 over 2 phi dot square minus the gradient of phi square minus m square phi square minus the potential. I have highlighted the terms partial sub nu, partial super mu, and phi dot square minus the gradient square because these are the ones that lead directly to the canonical momentum density. We start with the canonical momentum density for the field. It's defined as the derivative of the Lagrangian with respect to the time derivative of the field phi dot. So the momentum density is simply the time derivative of the field itself. Next, we construct the Hamiltonian density. The definition of Hamiltonian density is P phi dot minus the Lagrangian. This is the field theory analog of the particle Hamiltonian P q dot minus the Lagrangian. And finally, substituting the expressions for P and the Lagrangian, we simply have, step by step, this expression here on the box. This Hamiltonian corresponds to the Klein-Gordon field, a relativistic scalar field with positive definite energy. It's one of the simplest examples of how classical field theory connects directly to quantum field theory. The energy density of the field is always positive, ensuring physical stability. Pause the video here if you want to copy the full Hamiltonian derivation before we move on to the next section. Now we move to exercise number 3, where we are asked to find the conserved current associated with a global symmetry of a free scalar field. The Lagrangian is partial sub nu, partial super nu of phi, and the transformation is a simple shift of the field, phi transform phi plus alpha, with alpha a constant. This is a classical example of how Noether's theorem connects a continuous symmetry to a conserved quantity. Let's go step by step through the variation of the Lagrangian, identify the repeated index, handle the metric tensor correctly, and extract the final expression for the conserved current. We start by varying the Lagrangian. Since the Lagrangian depends on the field phi and on its derivative, partial sub nu of phi, the variation produces two terms. And this first term, partial of the Lagrangian with respect phi, is replaced using the Euler-Lagrange equation. That's why the variation of the Lagrangian reduces to the derivative term, which is the one we will now analyze. Since the transformation of phi is phi plus alpha, the variation of the field is simply delta phi equal alpha. This is the key point. The symmetry is a constant shift of the field. Now we look at the repeated indices again, nu and mu. Because of Einstein's summation convention, repeated indices imply a sum. The red ellipses show where we must be careful. We cannot repeat the same index incorrectly, so we rename one of them to avoid confusion. And again, to handle the derivative properly, we use the metric tensor to lower the index. This keeps the expression covariant and ensures the current we obtain is a proper 4-vector. Now putting everything together, the conserved current associated with the symmetry is J super nu equal to alpha partial super nu of phi. This is the Noether current for a free scalar field under constant shift. It's a simple but elegant example of how symmetry leads directly to conservation laws in field theory. Pause the video here if you want to copy the full derivation. Now to finish exercise number 3, we find the conserved charge associated with the current that comes from the symmetry of the Lagrangian. It's obtained by integrating the time component of J super nu. The time component is nu equals 0. So this is simply 2 alpha, the integration in volume of phi dot. This charge remains constant in time, confirming that the symmetry under constant field shifts indeed produce a conserved quantity. So this symmetry gives us a conserved current and a conserved charge, a direct confirmation of Noether's theorem for the free scalar field. Every continuous symmetry corresponds to a conservation law. And here, the invariance under field shifts leads to the conservation of Q. Now we move on to exercise number 4, where we extend this idea to a complex scalar field. The Lagrangian is given by this. It is the Klein-Gordon Lagrangian. Our goal is to determine the equations of motion obeyed by the fields phi and phi adjoint. This is the Klein-Gordon complex field, the relativistic scalar field theory. We start with the Euler-Lagrange equation for the field phi. This is the same structure we've used before, now applied to the complex scalar field. When we take the derivative of the Lagrangian with respect partial to, we again rename the dummy indices. That's what the red ellipse marks. This avoids confusion between repeated indices and index summation. Again, the same trick. We lower the index using the metric tensor J super nu rho, just as before. The derivative then gives us a Kronecker delta, delta super nu sub rho, which replaces one index with the other. Putting this step together, we find the following. And this is the Klein-Gordon equation for the adjoint field. A completely similar procedure gives the equation of motion for phi adjoint. So both phi and phi adjoint satisfy the Klein-Gordon equation, confirming that the complex scalar field obeys the same relativistic dynamics as the real one. Pause the video here if you want to copy the full derivation. Now we move to exercise 5, where we refer to the previous Lagrangian and calculate the conserved charge. From now on, the conserved current associated with the symmetry of the Lagrangian for the fields phi and phi adjoint is this. This expression tells us how the infinitesimal variations of the field generate the conserved current. Now, in the previous exercise, we already calculated both these derivatives. Let's go backwards. These derivatives here. So we can now substitute them directly into the expression for J super nu to simplify the current. Now we introduce an infinitesimal unitary transformation of the field, which is given by the exponential, which is by just expanding by Taylor, this expression here, and we stay at first order. So therefore delta phi is imaginary alpha phi, and of course delta phi adjoint is minus imaginary alpha phi adjoint. These variations represent a global phase rotation, the simplest example of a U1 symmetry, which will lead to a conserved charge associated with particle number. Now just simply substituting the above, from the infinitesimal transformation we introduced, the conserved current takes this form. This current arises directly from the global U1 symmetry of the complex scalar field, the invariance under a phase rotation. And as before, the associated conserved charge is obtained by integrating the time component of the current, J super 0, and we get this. It will depend, of course, of partial derivatives with time, the component J super 0. Here alpha is an infinitesimal real parameter. This charge represents the conserved quantity associated with the field's phase symmetry, the foundation of charge conservation in quantum field theory. And now we move on to exercise number 6, where we consider the electromagnetic action via the electromagnetic tensor here. And we vary the potential according to this expression here. A sub nu, we vary to A sub nu plus partial sub nu of phi, where phi is a scalar field. And we are asked to determine the variation in the action. The variation occurs through the electromagnetic tensor, given this expression here. This is just simply applying Leibniz rule for derivatives that we learned at school. This sets up the next step, analyzing how the field strength tensor changes under potential variation. Now we start by writing the variation of the covariant electromagnetic tensor. And we substitute simply the variation of the potential, the delta A sub nu, we substitute it by partial sub nu of phi, and we get this here. And it equals 0 because partial derivatives commute. We can swap between delta and partials. And similarly, for the contravariant tensor, we obtain a very similar expression, and again vanishes again for the same reason. The derivatives commute. And since both variations of the electromagnetic tensor are 0, the change in the action becomes, of course, 0. Therefore, the electromagnetic action remains unchanged under this transformation. This proves the electromagnetic action is invariant under gauge transformations, confirming the fundamental U1 symmetry of electromagnetism, the mathematical origin of charge conservation. It's a beautiful result. Symmetry and conservation are two sides of the same coin. Pause the video here if you want to copy the full derivation before we move on to the next. And now I would like to leave you with the poetry of the electromagnetic tensor, the silent harmony between electric and magnetic fields, the geometry of light itself. I hope you enjoyed it if you made it this far. See you in the next video. Bye bye.